Hello, everyone, and thank you for joining us today. Welcome to Megger's Testing Tactics webinar series. Today's topic is practical aspects of PED testing for cable condition assessment. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Robert Probst, Product Manager for Cable Fault Location. Also, to assist with the question and answer session, we will have joining us Henning Oetjen, Product Manager, and Charles Nybeck, Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, Robert.
Hello, everybody. Welcome to this webinar on the practical aspects of PD testing. So let me go through the agenda for today real quickly so you know what we will be talking about. So first of all, I will go through the theory of partial discharge testing on a very high level and very quickly so everybody is on the same page. Then we will discuss this description of practical aspects. So what are really practical aspects when it comes to partial discharge testing? We will go through test recommendations. We will take a look at the setup in the field, and we will talk about some result interpretation. And at the very end, just a few words on where are we going in the industry right now. So first of all, when we are talking power cables, medium voltage, high voltage, shielded cables, you probably know that cables look something like this. So underground cables in the trench just before commissioning. And I found another interesting picture where you can already see all the players in one picture. I took this from NKT. So you see the cable drum in the background. You see the cable is being pulled into the trench, and you see workers, right? And even there, you know, you might be able to spot a splice. So those are all the ingredients that we need to talk about practical aspects of partial discharge testing. So when it comes to this type of test in the field, it is essential to think about what components are you affecting during the test, or with which components are you interacting. And it's actually pretty straightforward. You have the main insulation that is there, that is the cable itself. Obviously, we have solid dielectric cable and paper cable with all the different insulation media, so predominantly XLPE. There is some EPR, and in the high voltage world, there's also these so-called high performance thermoplastic elastomers, or P-laser. And for the paper cables, you have typical pill construction, paper lead covered, MIND, mass impregnated, non-draining, or in the high voltage world, these polypropylene papers. This is one thing to consider. The other thing to consider is the accessories. So everything that is not coming out of the factory on that cable drum is pretty much an accessory, namely splices, or in European terminology, in British English, everybody is calling that joint. In the US, everybody calls that a splice. And you have end terminations. And very important, you will hear this repeatedly throughout the webinar. The accessories are considered to be so-called interfaces, layered interfaces. Just keep this in mind. This will come back later on. And then in general, you have 2 types of activity when it comes to a defect, okay? So the first or when we talk about activity here, I mean specifically the ignition behavior. So first you have anything that can be remotely described as a void or inclusion or something like that. So a concentrated defect in the material itself. So these defects, they have a very characteristic behavior. Their ignition behavior is pretty much a function of the maximum field intensity, or in English, the peak voltage. So you reach a certain peak voltage, that void will ignite and you will have partial discharge activity. And the other more important type of defect is an interface in general. The tricky thing here is that this layer of two materials, which then forms a surface between the two, that is subject to something called surface discharges when it is subjected to voltage. And these surface discharges, they have a behavior that is a function of the gradient, the rate of change. So here, the important thing is the frequency of your test voltage, very important. If the frequency is too low, you don't have any surface discharges or very, very little, and then you won't be able to detect the weak spot, the defect. And then also you can have situations where you have moisture ingress, because maybe your jacket was compromised during installation. Remember that first picture, when you pull the cable into the rock there, or the sand or whatever, and you damage the jacket, this is your point of moisture ingress. And if you have a defect and that defect is kind of wet, then you could have the situation that compared to what it should be, if it would be dry, you have reduced or no activity at all. That means you apply voltage and at first you don't see anything. So now in terms of PD testing, what is the purpose and what are the advantages of the method? So first of all, again, cable. You have two distinct things. You have the main insulation, the cable itself, and you have the accessories. Now, to get this out of the way, for the aging of the main insulation, the 10 delta test is a good test to actually measure the dielectric losses. And for anything else pretty much that you see here, for the accessories and localized weak spots, it is the PD test. That is the test that can actually treat these problems. So again, 10 delta, it's an integral or a global measurement. So that means, you're measuring pretty much the average temperature of a glass of water. You cannot know if one drop of water in that glass would have a different temperature if you just, let it drop into the glass. So it's integral. It's like the average over the entire insulation. By the way, including the accessories as well, because they have leakage and losses as well. And then for the local issues, you would do a PD test, and that PD test is able to localize the defects. Very important. The 10 delta cannot localize the issues you would find, but the PD test will be able to localize the joint issues, the termination issues, and isolated weak spots. Now, when we say partial discharge, what is this really? So I always, steal the joke from one of my colleagues that tries to convey it this way. This is a very complicated chemical molecule. But you can make all kinds of scientific descriptions what this molecule is. And you could also say, hey, this looks like, we would call it a football. In North America, I have to say soccer ball to be clear, right? And so that would be an easy description of what you see on the left. And we want to keep it at this level in this webinar. In simple terms, calling that what you just saw a soccer ball is the easy way to say it. And so you can pretty much very clearly define what partial discharges mean to something that is to somebody who is not a scientist. And it's pretty much a bit of energy that occurs at a spot that the designer has not intended to when he designed the cable and the cable system. It has very destructive behavior, a very destructive behavior, because it damages and then decomposes everything in its surroundings. Therefore, it initiates and then furthers an ongoing breakdown of the insulation until the asset will fail due to full insulation breakdown, which then means the life expectancy of that asset is reduced. And typical PD fault, you can see on the right, these tracking marks that will eventually lead to a flashover. So just in short, as a punchline, so to speak, you can say PD is the predator of insulation. And I guess a few people still remember this excellent action movie. So this is, you cannot run from this guy. So if you have PD in a solid dielectric cable, then it is only deteriorating and you cannot run away from it. Important enough here is, and very lucky for us, however, we can measure it. So it's not out of our experience. So we can actually measure it and then do something about it. In terms of failures, typical failures, just some pictures. So anything here would sooner or later lead to a failure of the asset due to partial discharge activity. So you can see incorrect sanding, incorrect cutbacks, pollution and contamination, cuts into the insulation, slipped off with the knife. So anything is possible. And believe me, everything is possible in the field in this case. These things exist. They're not just, some academic exercises. This is kind of what we see more and more in the field everywhere, specifically on wind farms. Now, in terms of general scenarios here, the cable laying, so the commissioning testing, is actually the most crucial part when we're talking cable and condition assessment and maximizing economic life of the asset. So when you look at the distribution of the faults that you have and you try to assign them to a certain type of action, then cable pulling itself, like what you saw on this first picture, to get the cable there into the material and then covering with more sand, actually filling the trench, that phase is significant for causing problems, mainly due to sheath damage, and then simply the workmanship issues. Remember, the cable is the cable, the accessories is where you put your hands on. So everything, whatever we do all around the globe, anything a human touches is prone to error. I mean, this is inherent. You cannot run from this. So, and this is one example for that. The mistakes happen when people work on the cable that comes out of the factory. Now, in terms of testing and standards, this is why we do not want to go into the scientific part of PD testing. There's an international standard that is very substantial, very deep, very broad. It's IEC 6270. It's pretty much the international go-to standard for PD testing, basics, explanations, test circuits, mathematical calculations of the different things the software is doing today. So, and again, very easy. There's two ways of doing PD testing. You can do it the conventional way, or you can do it the non-conventional way. The conventional way is you are using a coupling capacitor in a specified test circuit. You calibrate this test circuit, and then the unit of measurement will be picocoulomb. IEC defined picocoulomb. IEC also talks about frequencies, for instance, these things like center frequency, what is the weighting function and everything. We don't want to talk about this here. just as a takeaway message, there is an international standard that is substantial and that is, for a while now governing PD testing as a diagnostics tool. And if you do not do it this way, for example, you apply a lot of filtering that is not covered by the standard, or you measure in frequency ranges outside of the standard, or you do anything else, acoustic PD detection or corona camera, or sound or whatever, ultrasound, that is non-conventional. So you're only doing an IEC compliant test if you do the full program that is covered under this term conventional PD testing. Anything else is non-conventional. And the takeaway message here is that anything you measure by non-conventional means, massive filtering, different frequency bands, or ultrasound, corona camera, whatever, is not comparable to results that you have obtained by the conventional way. So you cannot just take the microvolts or whatever unit from an UHF and convert it to picocoulomb as you would have obtained in a conventional testing scenario. Very important. And then the way the method is localizing the weak spots or the partial discharge activity is very similar to TDR, time domain reflectometry, but not exactly. A TDR is always connected to one side of the cable, the near end, or then you go to the other side if you want to take measurements from the other side. So the start of the pulse is always one end of the cable. Now, the traces you obtain with PD testing that is using runtime analysis or the traveling wave method, as it's sometimes called, to localize the defects, they look very, very similar to TDR traces, but they're not exactly. You have to think about putting a TDR at the spot where the PD activity is. And if you think about then that some energy of the pulse is sent to the left and the other, typically 50%, would be sent to the right, and then traveling all the way to the far end, being reflected there, coming back to the detector. So you get two reflections, the so-called first reflection and the so-called second reflection. And so you can think of this as a TDR, which you would initiate it at the spot of the PD activity. That is the difference when you try to interpret these traces. Now, after this little bit of theory, to the practical aspects. So practical aspects are what technology are you using, which means wave shapes. Then testing regime and procedures. So what are you testing, when and how, and maybe why? Then the practical setup itself, you have to lay out a test circuit. And then how do you obtain and interpret the results that you get? So to the test program, again, talking about the cable itself. So you can pretty much classify, you have new cable. That is its own, application. New cable require commissioning testing or acceptance testing, or in IEC, it's always the after laying test. That's their terminology for that. And this test or this phase with respect to the lifetime of the asset has a major influence on how this cable will behave throughout its life cycle. So the economic life, including the return on investment that was initially kind of calculated for a project, is directly affected of how well you are doing the commissioning test. If you do it quick and dirty, you will never get the projected calculations, the projected profits, the projected return of investment out of your project. Nowhere near. Actually, it can be so bad. We see this in some sectors at the moment that entire banks struggle because, let's say, 10 years ago, they financed projects. Nobody paid attention really to do a good commissioning test. And now their return of investment and the profits are impacted every so often by severe faults that occur, that they have like kind of a backlash. They never get where they were supposed to be, and then that even caused some financial trouble of some of these banks that finance these projects. And then obviously banks, then they try to push the risk to the insurance company or something like that, but then the insurance company sits in front of this mess, right? So commissioning testing is of utmost importance. Then we have serviced age cables. There, this is the typical aspect for preventive maintenance testing, so periodic maintenance to drag out the life cycle of the cable as much as possible to maximize its lifetime, its remaining economic life. This is mainly done, as I phrased it here, to avoid outages, unplanned outages, unscheduled outages, which have a direct negative impact on these index numbers, which partially influence the budget of utility companies, more so in Europe and Asia than in North America. But it's important to have good performance index numbers. And periodic maintenance is pretty much to maximize the profits, meaning minimizing the outage minutes, so the asset will make money for the company. And then we have repaired cable. And this is only important in terms of operational integrity. So if you have repaired an asset, a cable, you want to do an after repair test. This can be a very simple, I will just do 5 minutes VLF to see if it holds. Or if you say, this was a fairly new cable, it had a fault, I built a nice splice. I want to see if that splice is really good, or if I just created the next problem down the road because that splice was not built very well, and in a year or so I will have the next fault. So this is kind of like in terms of economic life, to secure the profits. Okay, you had an interruption, you just want to make sure you have not set up yourself for the next failure right away by doing a good job, by implementing good quality. So as a punchline here, this is something I saw in a related presentation recently, and I liked that, where the people were talking about these financing aspects and return of investment. And so why should anybody involved in a wind farm project, solar project, whatever, care about quality? If you are an investor, or if you are the operator, or if you are the owner, or if you are a utility company with a lot of cable, or if you are the insurance company, why would you care? And I like this kind of proverb here, that they pretty much say, you know what, the bitterness of poor quality remains long after you had the sweetness of low price, because at that point it is forgotten that you had a low price and you have to deal with all of these quality issues. Now, talking about wave shapes. The standard wave shape for partial discharge testing is damped AC. It's an oscillating, attenuated voltage wave that lasts approximately a few hundred milliseconds. So it's a quick shot. It's obviously an AC waveform. There is a defined frequency band for that, which is the so-called IEC frequency range. That frequency range was established for the resonance test sets, the big resonance trucks in the, let's say, 1990s. And the damped AC waveform was the first that was qualified and investigated and found to be completely comparable to line frequency. So if you would be able to do it with 50 or 60 hertz stiff, which is not possible in the field because your machinery, your equipment would be gigantic due to the apparent power that you need to charge a cable. So for field testing, this waveform is the dominating waveform worldwide for about 20 years now. So we are at the point of 20 years of history with damped AC. So the frequency band is 20 to 30 hertz up to 500 hertz. The second waveform that is suitable for field testing is the so-called cosine rectangular VLF. That waveform was the original waveform for VLF testing, first available in 1986. Since then, we have VLF testing. And so for more than 35 years now, we have VLF testing. And it can be used for PD testing as well. And this was kind of a question of customers to us. Hey, you have this cosine rectangular waveform. It's nice for withstand testing, but can I do PD testing with it? So a lot of investigations were done, and it was directly compared to damped AC. And since damped AC was already found to be fully comparable to a line frequency test, cosine rectangular is then also fully comparable to a line frequency test. When you do PD measurement with this waveform, you have to correct it for the peak. Remember, you also want to catch the voids, not just the interface, the surface discharges. So you have to go a little bit higher in voltage to get the peak, but that's perfectly fine. And just as a comparison in terms of physics, very important, there is another waveform that you may find in the field, and that is the 0.1 hertz sinusoidal VLF. Now here on this picture, you can already see what the problem is. The problem of this waveform is that it doesn't have the gradient, the rate of change of voltage, which makes damped AC and cosine rectangular comparable to line frequency. That is missing when you do sinusoidal PD testing. And it has been found in many comparisons and case studies in the field. There's earlier webinars where I showed this data. So if you want to go back to those webinars, you can see some of these case studies. There are very, very many by now, where these waveforms are not producing the same results. Cosine rectangular is damped AC, and the sine wave is the odd one out due to that effect. You will find voids if you go high enough with the voltage, obviously, to reach the peak voltage, but you do not have the gradient, the dV/dt, to initiate the surface discharges. So using 0.1 hertz sinusoidal is not recommended at all for PD testing. Now, in terms of test programs, okay, so again, newly laid cables. On newly laid cables, commissioning testing, serviced aged cables, preventive testing, and after repair as an operational integrity test. Focusing on commissioning testing now. Think about this. Remember the first two pictures. The cable comes out of the factory. Supposedly, the cable manufacturer has quality processes in place. So he's doing all the partial discharge tests that he should do in a Faraday cage or double Faraday cage to levels that you will never be able to reach in the field. And he says, this cable reel is perfectly fine. It's shipped to you. We assume nothing happens on transport, during transport. You take it off the truck and then you start laying the cable. So this is the moment where damage can occur. First of all, again, sheath damage, so jacket damage. The jacket integrity can be compromised, which is important down the road because any sheath fault is an entry point for moisture, and moisture ingress will damage your cable sooner or later. And by capillary effect, this moisture will travel through the cable over time. It will take time, but it will not just remain near that the cut or the hole or the crack in the outer jacket that you have caused by pulling it against an object or exceeding bending radius or whatever. And then you put your hands on the cable, so you build the splices you put on the end terminations, again, layered interfaces. Remember, surface discharges, use the correct waveform. And so your commissioning test should be carried out in a way to focus on this area. So you are focusing on the general integrity of the insulation, the integrity of the outer sheath, and the integrity of your joints, or of your splices. So the recommended best practices, you should do a sheath test. I know it's not very popular in the US, but it's up to you to determine if you need to do it, if you should do it or not. It's definitely part of kind of the global best practices, if you want to call it like that. So all around the world, people are really, really meticulous in terms of sheath testing. They want to make sure that the cable does not have any parts where the outer jacket is compromised. You do a withstand test as per the standard. That will find you all the gross defects, and this is kind of a safety test, so you can re-energize and it's not push and pray, it will not fail. And the new thing, which is, to be honest, nowhere in no standard in no country a mandatory test yet for commissioning, but we are on the way. A few years into the future, you will see that country by country, standard body by standard body will slowly go down that route, that at one point it will go from a mere recommendation to a commissioning test shall contain this. And the partial discharge analysis test, the partial discharge test will find the problems in your joints. Again, we have various standards for that. For the voltage test, VDE, Senelec mainly, and in North America, the IEEE 400. For the diagnostics, again, you have two technologies, right? You can use damped AC or cosine. Now, if you want to do your withstand test first and then the PD test afterwards, you would use damped AC. If you want to combine both into a so-called monitored withstand test, then you would do that. Don't confuse these two. If you do a withstand test and a damped AC test afterwards, the damped AC test is a diagnostics PD test, a full proper diagnostics PD test, which you do in various steps. A monitored withstand test is pretty much a withstand test still, but you trending an additional quantity. And that quantity, the only quantity that makes real sense, is the PD activity. So you keep the cable at test voltage level, and you see over time, do I see certain splices having PD activity, and is this PD activity increasing over time during the test? So that is the recommendation. Now, in terms of global issues, we talked about these, the insulation is still there, right? That's the actual cable. Just to have something said about the 10 delta test here. On new cable, we're still talking about commissioning cable here, acceptance testing. It is not recommended at all and discouraged actually to do a 10 delta test on new cable. The reason is today all of the cable is copolymer cable, tree retardant XLPE cable. And these cables, they show a certain behavior long before you can actually call them aged. So when we're talking tree retardant XLPE and you say aging, we're talking 15, 20 years. Before that, it's not aged, forget it. So, the time to call a cable an aged cable, we're talking something around 15 years here, approximately, as a rule of thumb. Now, before that, the cable shows a different dielectric behavior as well that has nothing to do with aging. It's simply chemical processes, because you have inhibitors in there and additives, acetone and all of these things to prevent the water trees from forming and growing. And that has a significant influence on the dielectric behavior. And you will get misleading results, you will get results that are sometimes completely, out of scale. You expected number X, Y, because maybe you read it somewhere that a cable should have this, but the number is completely gigantic, and then you may think, oh, the cable is bad or something. No, modern copolymer cable shows a complicated aging behavior, and if you really want to do a 10 delta test, if you really insist, I want to do this, even though it's useless, it's ineffective, you should wait until 1 year. Okay, so the cable should be in service under load, not just sitting there for a year. It should be in service under load for at least a year to prevent initial disaster. And a lot of customers that we see, they don't really care a lot about 10 delta testing, especially, if your asset manager is quite technical and he understands cable, he knows about this. I mean, this has been published many times. This is nothing new, that copolymer cable shows this behavior, and that a 10 delta test on new copolymer cable is very questionable or ineffective. And a lot of our customers that we talk to, they don't do anything down that road before maybe 3-5 years. Some even say, no, before 10 years, I'm not worried about 10 delta. So keep this in mind. The important test for commissioning is the partial discharge test. Again, just a summary for the commissioning test. Just in short, sheath test, highly recommended, has a lot of value, especially long-term. Withstand test as per the standard. The workmanship test is the PD test, revealing assembly faults. Use a voltage that produces results comparable to power frequency, damped AC or cosine. Avoid sine wave for PD testing. And if you are under time pressure, or if you think that a VLF plus a PD test is too slow, or you want to do it in a different way, you can consider as an alternative a monitored withstand, where you do both at the same time. You just trend the PD during the withstand test. Now, in terms of setup, okay, so we talked about what to do in the field. We talked about the waveforms, the technology. So how to set it up? So first of all, the way you do the test is, remember, like IEC, you calibrate the circuit as per IEC. The next thing is, in your software, you kind of initiate the PD testing equipment, but you don't put on any voltage, you don't energize, you just record what your PD detector gets back just by listening. So you're just listening. That is called disturbance level or background noise. And practical experiences show in typical environments, 100 picocoulomb is a very respectable background noise. You rarely see less. If you're lucky, sometimes maybe very rarely 50 or 80 or something like that, but 100 as a rule of thumb. If you have a high noise environment, that can be also much more. And then you energize the test equipment, and you go from step to step, take a few shots if you use damped AC, and record what you see. So important is to take a few steps below operating voltage U naught, just to see if you have activity below operating voltage, which would be a critical condition. Since then, it means that if the cable is energized, you always will have PD. Then you take measurements at U naught, because that is the critical point where the so-called discrimination happens. So the making or telling the difference between a critical condition and a condition for further study, or where you say no action required. You try to find the partial discharge inception voltage, and if you have inception, you also want to find the extinction voltage to see if you have a PD event, where does it extinguish. Then a typical practical aspect here for the setup is, okay, so how far can I even see? I calibrate, so what is my measurement horizon, so to speak? The traveling wave method is object to typical TDR limitations. So you suffer attenuation and dispersion with the pulses, with the signals. And it really depends. Just as a rule of thumb, very, very average, 5 kilometers. We've had cables where we measured far beyond that. And then we had very short cables, 1,500 feet, where you could not even see the far end of the cable because the attenuation was so high. So it really depends. Pill cable typically, so paper insulation has a much higher attenuation. So you typically see much further on XLPE cables than on pill cables. If you have moisture in the cable, that can affect that. If you have a lot of splices, because each splice causes a reflection of these pulse propagation events. So you have energy loss there. So a lot of splices diminish your measurement range. The neutral construction can have an effect. And so the only way to really make sure that, how far can I see? Do I see the far end? Is a proper calibration. You know when you calibrate. Typically, you would say 1,000 picocoulomb is a good starting point. But if 1,000 picocoulomb for your calibration pulse is not enough, you can go higher. And if you have to do 50,000 to see the far end, well, then you have to do 50,000. Obviously, then, your signal to noise ratio is affected by that, because it's a big difference if you can see the far end of the cable with 1,000 pico compared to 50,000, for example. I'm just saying, don't stick to certain numbers. Those are just starting points, okay? A good guideline. If you have to do what you have to do in the field, and if you have a situation with high attenuation, you have to react. You cannot say then, oh, the calibration is no good, I have to go home, right? In terms of grounding, very, very important. That is the most common mistake you will see in the field, that the entire setup of the grounding layout is insufficient and just causes problems left and right. So first of all, here a vehicle, this could also be a cable test van, this could also be portable equipment. You are in a station, you have maybe a common ground bus running throughout the station, and then people, let me just connect to the nearest station ground point, and then they run the high voltage cable to the termination for the cable under test. They put the operational earth, the high voltage return, to the ground there, and unbeknownst to them, or hopefully they should understand that, they have created a giant ground loop by that. And a giant ground loop like this acts as an antenna. So you are collecting noise and noise and noise. You would not believe how much noise you collect there. So you do not do it this way, you do it this way, okay? Then you minimize the antenna effect. And remember, the coupler is very close to the termination where you connect to, very close to the connection point. So the filtering, the IEC filtering that the coupler can do, that is okay. So you can suppress any kind of noise there, and you minimize the distance to the range from the coupler to the connection point itself, a few meters of cable, where you can have any kind of interference being picked up. So now in terms of setup, a few pictures, field experiences. So this, for instance, is a proper setup. You see the PD coupler, you see the source behind there, that's the gray box there, that's a damped AC test set. And the high voltage cable, a shielded cable, goes into the coupler on the other side, and an unshielded high voltage cable comes out of the coupler, and you connect it with a proper, in this case, it is a proper connector for this type of switchgear to the cable. You run the ground to the local station point as you see it there, and this is a proper setup. So something not so okay would be the picture on the left. You just created a jungle, wires running across, looks like the rainforest, and you violated clearances, because that section that you see there from that red crocodile clamp, the red battery clamp, to the point of where the shield of the high voltage cable splits up into high voltage and the shield itself, that touches the frame of that switchgear. So that causes problems just right there. You could even have a breakdown there of that cable, a flashover, if you go high enough with the voltage. And this whole arrangement where everything is not really nice. So compare this to the right side. The high voltage cable is suspended in the air, so homogeneous field distribution, not near any grounded planes, not touching anything, clearances, as I said. And so that is a proper way of doing it. Here is an example from Italy where you see, again, cable is suspended, and sometimes it can be easy means, right? You take one of these, they had one of these plastic posts there, and we use this to suspend the cable there. You connect it, there in the middle is your connection, and you run the proper ground connection, and you will have good measurement results. Another pitfall would be, in this case, it was kind of okay, but generally speaking, this type of trick in the field does not work very well. The main thing for you is clearance, 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 clearance. If you don't have clearance and you can bend the other cables in a switch gear nearby, let's say you disconnected the cable from the switch gear, and you can bend it back to you and make room around their clearance, that is far better than trying to put rubber boots or rubber blankets, because you will have surface discharges there, since this is kind of electric field in the presence of matter, to be a little bit more on the theoretical side here. So you have a displacement there, field displacement, and that can cause surface discharges there. You meant well, you had good intentions, but you made it worse. In this case, it just worked out. Then some other good examples: PD coupler close to the switch gear. You use the connector to make connection to, in this case, A phase. The high voltage part, this is just approximately, how much is this? 5 feet of high voltage cable is in the air, not touching anything. The ground connection is very short, properly done, very good. Or here, now here you would say, wait a minute, where's the PD coupler here? Here we see a variation of PD system that is increasingly popular with people. They say, you know what, we know all of these splice faults, these assembly faults, they are in the hundreds and thousands of picocoulomb, right? So do I really need to measure down to 90, 100, 110 picocoulomb when I know that I will definitely be able to tell a splice problem in the field if I have a background noise that might be a bit higher? So customers ask us, hey, can you make systems with internal PD coupler? And so we have this in the portfolio as well. In this case, this is one of these vans. That PD coupler that you saw here is in the vehicle. It is installed in a way that you don't have any significant corona. You have a little bit more background noise with this test setup, so you're losing measurement accuracy. But the customer said, I don't care. My policy says I do not take any action until X, Y, Z values. So I can have more comfort and more safety because I don't have to make a special test environment here with, like, kind of preventing people from entering the area by putting up tape or whatever. It's touch proof, so to speak. And this is kind of trading measurement accuracy for comfort, and it's a trend. Definitely we're being asked more and more for this type of system with internal coupler. And then we have another example here in the field. You can see, again, there's the coupler, the high voltage cable comes out, and then you can see in the middle picture how it is connected to the end termination there. Again, suspended in the air, not touching anything, so the field around it, it's not distorted. On the very top there, you see some corona preventing add-on there at the very end. It's kind of like a spherical add-on that you put on the connector there that prevents spitting and corona. And then here, obviously, you also have challenges in the field, right? Everybody knows this. I mean, I've seen similar pictures in the US as well. So sometimes it's not so easy, but you can make this work by using a proper T-body there, or like elbow connector, and to have a low corona, a low connection PD connection there as well. That it's definitely doable. It might not be perfect in every case, but there are ways of getting it done. So just as a summary in terms of setup, grounding, low inductance grounding, clearances, keep the high voltage cable away from grounded parts, grounded planes, make sure your connectors, your multi-contact MC connectors are locked in so you have good connection. Typically, the coupler, put it as close to the connection point as possible. And if you think, well, I don't need like very precise measurement accuracy, I rather have some comfort as well. There are also van-based systems, vehicle-based systems with internal coupler. Avoid pitfalls. You just saw ground loops, corona by making a poor, like edgy connection with sharp edges. Avoid using rubber boots to cover adjacent parts or rubber mats. It's better to have clearance, 15 to 20 centimeters, depending on, so 2 to 8 inches, depending on the voltage level and how tight it is really in the cubicle. Don't let the unshielded part of the leads be on the floor. And if you have to use a support capacitor because your cable is very short, make sure the capacitor is on the right side, so it's on the side where the PD coupler can filter. Otherwise, you will get distortions from that coupler, from that capacitor as well. And now the last point, the results. So we talked a lot about this and that setup, what to do, how to test it, what does the setup look like. So, but what does the data look like? So the typical data that you have at the end of a PD test is this. So you put into the software various information, header information of the cable, just for record keeping and database and GIS information. And then you put in some electrical parameters, if you know them. Hopefully you know them: insulation, cross-section, where are the splices. And then the software will give you a representation of the cable. You have a calibration, so you can actually detect magnitudes of a partial discharge activity in picocoulomb, and you have your overall length. And then you apply the test, monitored withstand or damped AC test, and you get this data points, activities that were localized to a specific spot. And now, after all of this, you already know, if you have no information on the cable, you don't even know where splices are, by looking at the count. So on B phase here, approximately at what is this, 500 feet, we had a count of 40. So 40 events from a very few shots. It only takes a few seconds, a few minutes, a couple of minutes to do this damped AC step test. You got this kind of activity, and magnitude-wise, you see 3,000 picocoulomb, right? And around 2,000 feet, you got a second set of data for, in this case, it was measured on A phase. And the highest data point was more than 8,000 picocoulomb. And most data points reached 3,000, 4,000, even 5,000 there. So this is significant. This is a very high number. And you can pretty much say, even if you don't know where the splices are, these two things with a very high probability are splices, even if you don't know where they were or that they were there, because it is most likely an accessory problem, which means splice. So this is the data you see. And then in terms of how to kind of evaluate this data, so you always look for the inception voltage. If you don't have inception, that means the cable is PD free perfect. If you have inception, then you need to look, okay, where does the PD activity go out? Where does it extinguish? Because let's say inception is above operating voltage, good, it's not so critical, but extinction is below. That means once you have a PD event, it will be present from that moment onwards during operation, because operating voltage is enough. So that would also be a critical situation. If you have both inception and extinction above operating voltage, it is kind of like the situation, further study advised, keep an eye on it, but don't panic. You want to record the PD level at operating voltage, very important, and you want to look at the count, at the concentration. It's a big difference if you have only a few pulses being recorded, or if you have, as you saw in the picture before, that you have 70, 80, hundreds, 200s, 500 pulses recorded, because that is a significant concentration. To give you and to show you some guidelines, and keep in mind, evaluation and risk assessment is more than just taking a number and judging just by the number. You need to take into account what type of splice technology do you have, heat shrink, cold shrink, whatever. So all of these things have an influence on the final decision. But in terms of just the measurement data, this is the German guideline from like the German equivalent of IEEE for judging PD activity. So you see on the top, if you have background noise 100 PC or less, and you have no PD, very good. If you have PD at operating voltage or below, it's a failure. So that is a critical situation you need to deal with. And then you have this in-between state. Here, they pretty much say, well, you should come back in 1 or 2 months and do a repeat test. If that passes by showing no PD at 1.7 or higher, you're okay. If you have PD again, it's a failure and you need to take further steps. Another thing is that comes from a German utility company. So they do a similar thing. They know what cable they have in the network. Their risk assessment matrix and asset management program is tailored to their network because they do a lot of testing. They do hundreds of PD tests every year. So they pretty much say, we say a cable is damaged when PD is present. Doesn't matter at which voltage level, we call this cable damaged if we see PD. We say it's severely damaged if we have PD at or below operating voltage. And then they pretty much say, okay, where's my inception voltage? How high is the magnitude that I measure? What is the concentration? There, the discriminator is 1,000 picocoulomb, and they also take into account what is the importance of the feeder. And then you get something like this. This is a first approximation of a decision-making process. That's what they found for their network, which works for their cable, and they pretty much say this is how we schedule then our actions. Another customer feedback that we have is, and I would call them the strictest utility company in the world, because initially when they started testing for PD, they had insanely strict criteria. They loosened up on those criteria a little bit because they have now so much experience, gathered so much experience, that they saw that we can get away perfectly with being a little bit more lenient. So their PD thresholds for splice here, you see on XLPE is 1,000 picocoulomb. So they won't take any replacement action below 1,000. And if you have mixed cable, they found the same threshold, because their argument is, which is scientifically and technically correct, pill cable is much more tolerant for PD, since the oil has partial self-healing properties. So it's probably the XLPE part that we have to pay attention to. And yeah, so this is how they discriminate. What kind of action do I have to take? And then we have gathered together from what we have something that is called a diagnostics and expert user group. Then we have seminars, case studies done together with customers. If you put all of that into a similar table, you can pretty much say, again, new cable PD free up to 1.7 or 2 times U naught. That must be the goal. New cable PD free. If you have serviced H cable, again, end terminations or splices, the threshold 1000 picocoulomb, and for pill cables, 20,000 PC scattered should be looked into, 5,000 PC concentrated because there might be a dry out or tracking along the paper, and so forth. So we have over the years we have gathered some good recommendations as well. And then just to give you an idea about like the risk assessment matrix here. So when you have these values, you pretty much know a splice is 1,000 or let's say 5,000 picocoulomb. So what do I do now? Okay, do I take action or what's going on here? So you have to come up for your network with a matrix that gives you decision criteria, condition that you measured over importance. Obviously, more important cables need more attention. Less important cables need less attention because the associated risk, outage minutes, penalties, all of this is less of an issue. So you can pretty much come up with a general, recommendation or suggestion that you can say a cable that is of high importance, that is in perfect condition, you should still monitor this cable regularly by periodic maintenance just to catch any deterioration early on, so you're not surprised by it. If a cable is of average importance, so not a feeder cable that doesn't have a backup. So let's say if your installation is violating N-1, but in this case you might have a backup. So you say it's a big cable, a long cable, but I have a backup, so it's not as critical. And it has a condition of critical, you still need to do repeat measurements if you do not want to take action right away and say, well, let me be on the safe side and do something here right away. If you say, no, it looks bad, but not I don't want to take action immediately, then you have to do at least repeat measurements frequently to see if you're running into a severe deterioration of the splices that you saw PD activity in. So that is pretty much the level of the asset manager, that this is eventually what you create, what you have to come up with. And this might be different between utility companies. Okay, some might have a lot of more critical cables and they're a lot more prone to take early action, and some people only have very few critical cable. They have redundancy N-1, for instance, so they say, yeah, I do periodic maintenance, periodic testing, but not as frequent. And when I do it, I only focus the high importance cable. So it depends. There's not one fits all answer here. So that was it. And for the presentation, and now I think we will go to the Q&A session, and I will give the control back to Michael.
Robert? So at this time, it looks like the presentation portion of our webinar has concluded. We'll now take some time to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the GoToWebinar control panel. For those of you that are leaving, when you close the webinar window, a survey should pop up on your screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there's a field where you can also request a demo or a quote on any Megger products. As a reminder, a copy of this presentation, certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars, as well as register for upcoming webinars on our website at us.megger.com/webinars. Our next webinar will be this next Tuesday, where we will cover understanding proactive cable maintenance programs and the testing behind them. So let's jump into our questions. The first one I have, I'm going to direct over to Charles Nybeck. Charles, good morning. From what length and section can the partial discharge test on cables be performed? There are critical power cables that connect the power transformers to the medium voltage main bus, whose lengths are between 20 meters and 100 meters.
All right, thanks, Michael, and good question. So there's several different variables to the length at which you can test. There are some limitations on shorter lengths where you may be able to determine if you have partial discharge activity, but may have difficulty localizing it, and that may be more on the 20-meter side. Certainly, I don't see any issues with a 100-meter long cable. But as Robert said and mentioned in his presentation, really the best way to determine your limitation on length is to calibrate the test. There are several different things that can limit the test or the length of test or cable you can test, such as the number of splices, the type of cable, whether it's PILC or XLPE. As Robert had mentioned, there's difference in attenuation between those, the condition of the neutral, as well as the cable condition as well. So there's several different aspects there. But as far as the 20 meter to 100 meter, I certainly don't see any issues there. You can go much further than that. But I don't see any issues with that. But the best way to determine the I guess the validity of testing a cable is to calibrate that cable and see that you can see both the near and far end, and you should have some idea of the accessories or splices in between there as well. So I don't see any issue with testing those cables.
Thanks, Charles. While I have you, this next question is also for you. Are there advantages to performing conventional PD testing versus non-conventional PD testing?
All right, yeah, good question. So this is heavily application based. So as Robert said, the only method that can be or that can represent the measurement in picocoulombs is the conventional method, in which you're actually measuring that apparent charge. So that's the real advantage to performing the test in accordance to the IEC 6270 with coupling capacitor and measurement impedance, as Robert pointed out in his measurement circuit that he showed. Now there are several other ways of testing. I mean, in specific to cable, one that's common is testing, kind of online testing through HFCTs. The advantage there would be that it's an online test, I suppose. But there are different applications for different measurements, such, there was UHF was mentioned. UHF is a common measurement for GIS partial discharge, right? And that just happens to do with the gas physics there, and I won't get deep into that. And acoustic measurements are used for location of PD. So there are certainly advantages to using non-conventional partial discharge testing, but in terms of determining the condition of your insulation, the coupling capacitor or the conventional method with the coupling capacitor and measurement impedance to achieve the picocoulomb measurement of discharge is certainly one of the most advantageous.
Yeah, just to add to this, as Charles explained, this is application heavy, and also it's pretty much determined by the asset. So cables are fundamentally different from any other asset that you find in the power grid, right? Because they are distributed assets. They run for miles and they are not concentrated in one point like a transformer. So most of the non-conventional testing is, kind of, was invented for substation equipment, let's say for transformers, for end terminations, and for switchgear environments with short runs, where you can still pick up high frequency components of PDs and where you have access to the shields and everything. So for this, you have a non-conventional PD analysis. The offline PD test, conventional, done in the conventional way, is for the method for power cables, and it's the only method where you can really do a condition assessment, because you're actually measuring values that can then be used for trending, replacement programs, all kinds of things like that.
All right. Next question's over to Henning. Henning, do you also discourage acceptance tan delta for EPR cables?
Well, the basic problem is the same as tan delta testing on XLP cables. On any of the solid dielectric cables, you have additives added during the manufacturing process, during the extrusion process to be specific. And these additives are also dielectrically active when you test them. And tan delta test is a dielectric test. You measure dielectric properties of the insulation, but in this case, which also contains these additives. So when you do a measurement on a brand new cable, whether it's XLP or EPR cable, you will invariably, you will be, your measurement will be influenced by the dielectric behavior of these additives, and you will measure that effect. Typically, how it shows up is you get a absolute tan delta value that is much higher than what you would expect for the pure solid dielectric insulation. And that's what gets some people then concerned, and say, well, the cable might be not good. It really has nothing to do with it. And that's why, the best practice is do not even try to attempt to do a tan delta measurement and interpret it in the way that unfortunately some people will do it as a bad cable, but don't do the measurement and wait with this test, maybe at least to like Robert was saying, a year into the service, but under load. So eventually these byproducts will burn off, and then you get a true indication of the dielectric losses in that insulation.
All right, thank you, Henning.
Okay.
Over to Robert. How do some in-field testing companies claim to detect PD down to 5 picocoulombs on cables and accessories? ICEA S94649 asks for 5 picocoulombs as the limit on cables. Is it the same in the field?
Okay, this is an interesting question. Let me start with this. We know from decades of experience, and I just don't say Megger, there's other companies as well, the utility companies, the service companies. If you have a defect in accessories, this is in the hundreds of picocoulombs, in the thousands of picocoulombs. I just showed you an example from a real cable during the presentation. So there's no doubt that you will see it. Typical background noises in the field, which you cannot do much about. You can only optimize your setup, as I showed you. But if you have 100 picocoulomb background noise, you have 100 picocoulomb background noise. And that means if there would be a defect that is less than 100, then you won't be able to see it. But that is not the problem, because we know from practical experiences, you saw all these values from the utility companies, and they know it better than anybody else because that's their money, right? So they sign this with their blood, that this is not necessary. So we will be able to detect these defects. Now, in terms of the magnitude itself, here we're talking IEC picocoulomb, and IEC 6270 defines your frequency bands and where do you measure, how do you measure, what do you filter, what can you not filter, all of these things. So on top of that, these tests, like for instance, the one that you mentioned, that is a factory test. So that has to be done in a shielded room or a double shielded room even, and is typically done to different test parameters. And there you can reach picocoulombs. In the field, you cannot, if you do an IC conformant test.
All right, over to Henning.
Maybe I just can add one thing to it. You know, these factory tests, according to IEEE also, for accessories and for the cable in the cable plant or the accessory factories, they follow IEC 6270. But they have to, in order to address this issue of the background noise that Robert was talking about, they do it in a Faraday cage. All the measurements are done in a Faraday cage. So if we could do a field measurement in a Faraday cage, then we wouldn't have this background problem, and we could see these PD levels that you see in a factory. But we cannot put a Faraday cage in a field test environment, and that is, I think, is very important to understand. I cannot measure something under certain circumstances, like in the factories under Faraday cage following IEEE 6270. And use the results in the field where I don't have the same setup. Okay, that is where the problem comes in when people, and to be frank, it's one company that claims this, and there is nothing wrong with the measurement. It's just like Robert was saying, you cannot compare measurements that are not taken under the same test protocol.
Thank you, Henning. While we have you, the next question is also for you. During design stage, how do you know the length or which splice shall be accessible for testing if test distance depends on many variables?
Okay, well, from a design point of the circuit, you have two ways you can measure partial discharge. One is that you basically get the signal, the PD signal, traveling on the conductor of the cable, and then that's what we showed you today online at the offline testing with the coupling capacitor connected. And so with that method, I think Robert was showing you, we are limited to about a length maybe of 6 kilometers somewhere. So within the 6 kilometers, wherever the splices are, doesn't really make a difference, okay? Because you don't need access to the splice. Now, the other way, if you have cables that are maybe 20, 30, 40 kilometers long, you obviously cannot localize the defects using this type of technology, the one-ended measurement, what we call it. But you can measure you can measure PD in splices if you make the splices accessible, but then you don't measure in the conductor, but you measure the PD in basically the metallic shield or the ground patch from the metallic shield to the grounding system. And you put couplers, you decouple the signal out of the let's say the metallic shield at these accessible points where you have the splices. So it all depends, how long the cable is, and if it is very important that you can measure each splice, then you have to make each splice accessible. But like I say, that's more typically the situation when you have transmission cables, where this is frequently done, where you're really only interested in the splices. You're not even interested in the cable PD, because honestly, you couldn't measure cable PD because the cables are too long. Okay, you can measure from a splice several, maybe 20, 30 feet to each side of a splice, but you cannot measure into the cable anymore. So there are limitations because of this, and that can be taken in account when you make the design of your circuit.
Henning? Next is over to Robert. Robert, regarding testing distancing, I believe there was a recommendation on the bottom of the slide. Could you please elaborate on the rule of thumb?
Okay, so this, Henning just touched on this. This rule of thumb is the technology, the one-ended measurement. Now, this number, this is why I said take it with a grain of salt and it's only a rule of thumb. If you have a very well-built XLPE cable, the splices are all built very well, there's no water ingress. We've had cases where you exceed far into higher length, where you were able to measure far beyond 5-6 kilometers. We have had one example fairly recently, where our field guy was able to do a calibration over 13 kilometers. But then you have these cables, and maybe the next time we talk about this topic, I will try to find screenshots of that from the calibration trace. When you have a high attenuation situation, for instance, typical situation, mixed cable, a certain percentage XLPE, but still a large portion of PILC, of paper lead. So the paper lead is dominating that entire circuit. And sometimes, especially if it's very old paper cable, you have such a high attenuation that you can't even see 1,000, 1,500 feet into the cable. You will see maybe a very small blip at the end where the cable end is, that reflection from the far end. And you have a cable that is 4, 5, 6 kilometers long, and you see the end reflection much better because the situation of attenuation and dispersion is much better. So this is why it's a rule of thumb. It really depends on the cable that you're trying to test. So this is why it's so important to do a proper calibration, which you then save, and the software is using that calibration to determine the magnitude, the apparent charge of the PD event, and where it is to localize it. And your calibration will clarify all of these questions. If you put into the calibrator, let's say 1000 picocoulomb, that's a typical standard setting, and you see a good end reflection, well, then you will have no problem carrying out a very good test. If you don't see the end reflection, then the next step is, okay, I will try maybe 5000 picocoulomb for the calibration. And then you might see the end reflection. So this is why it's a rule of thumb. It really depends. A number of splices, moisture ingress, insulation material, big time, has a big influence on what the true value really is. But on average, you can say 5-6 kilometers. So if you have a 10-kilometer cable and you can't see the end, but you think you can see 4 or 5 kilometers into the cable, you go to the other side and you measure the other portion from the other end, for example.
All right, our next question is going to go over to Charles. Actually, it's not a question, it's more of a comment we got from Dennis. Dennis had mentioned that it is important to note that a transient could start a PDIV above normal line to ground voltage. So, if PDEV is below normal line to ground or even close to it, one would be in trouble. Charles, I know you wanted to have a comment on that.
Yeah, so thank you, Dennis, for pointing that out. That's a very important point and kind of why I wanted to comment on that. So the PDIV and PDEV are two very important measurements when performing partial discharge testing. And those are the partial discharge inception voltage, which is the voltage at which partial discharge starts to take place, and then the extinction voltage, or PDEV, which is the partial discharge extinction voltage, which is the voltage at which the partial discharge ceases to happen. And these are not always at the same voltage as Robert had mentioned and Dennis pointed out. So if your inception voltage is above the operating voltage, one may think that everything is okay and all is well, and more or less that's true. But if the extinction voltage is lower than the operation voltage or the operating voltage, then, as Dennis pointed out and as Robert mentioned earlier in his presentation, then, switching or a lightning strike, something that causes a transient in which your voltage, your operating voltage then exceeds the inception voltage and you have partial discharge start to take place. Well, since the extinction voltage is below the operating voltage, once that cable settles back down to the operating voltage, then that partial discharge will continue to take place and then start deteriorating the insulation there. So it's very important to, when performing offline partial discharge testing, to take both the inception and extinction voltage measurements, as this condition may happen, and one may think that the inception voltage is above operating and everything's okay, and then one day the cable fails due to partial discharge because the extinction voltage was below that. So really good comment, and just kind of wanted to elaborate on that for anyone else as well.
Thank you, Charles. Our next question is going over to Robert. Robert, what is the best cable test, AC or DC?
Okay, that's a very broad question. So when we're talking withstand testing, because this is like, cable testing, then there has been a paradigm change over the past few decades away from DC to AC. So typical power cables, you test with AC. There's several reasons for that. DC testing is okay for paper lead cables, so for oil-filled cables, because the oil is the insulation medium. It's partially self-healing, so the DC stress doesn't cause any like lasting effect, negative effect on the insulation. And this is why it's still recognized by various international test standards. And they say, if you have old paper cables and you want to do a DC test, that's okay. Even though the AC test would be more beneficial to actually find certain faults for sure, because that is the second point. After it was found that DC causes damage to solid dielectric cable, there were also investigations on how good a DC hypot test is in finding and bringing certain types of faults to a flashover. And while the AC did very well on these tests, finding a lot of faults that were introduced to the test samples, the DC did not very well. So from today's perspective, the go-to cable test is an AC, and in this case VLF test, for the benefit of having a small equipment. And also obviously the partial discharge test is done with an AC test with a near line frequency AC wave shape.
All right, thank you, Robert. Last is over to Henning. Henning, is the measurement the charge prior to the discharge? The earlier the chart looks like TDR. Can it give approximate location of the PD?
Well, maybe I'm not totally understanding the question, but let me just say this. You can, once you have partial discharge occurring, that is when the discharge occurs. You don't have a charge prior to having a partial discharge. That is different than in the TDR measurement where I induce a pulse. In the PD measurement, the pulse, I don't induce any pulse and measure it. The pulse is induced by the defect in the cable, so I cannot get a measurement before the event occurs. When the event occurs, it creates a pulse, and that's why I I need the measurement of two pulses to get the timing difference, so I can localize the defect. Okay, so I hope that answers my questions. Otherwise, maybe the gentleman can rephrase his question a little bit, and we can try again.
Yeah, and you are all more than welcome to reach out to us offline for any other questions that we didn't get to today, especially seeing as that we've run out of time for our Q&A session today. Again, we're sorry if we didn't get to any of the questions that you asked us here. We had a lot of really good ones. We unfortunately just ran out of time today, but we'll be working to follow up with you offline because, again, very good questions and we don't want to leave them hanging. But as a reminder, we will be sending out a copy of this presentation, certificate of attendance, and a link to the video recording of the webinar in about 2 business days. I'd like to thank you all for attending, though. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once again, I'd like to thank you all for attending, and I hope you all have a great weekend.